Thanks, Jared. So I was going to start by saying thank you to the organizers for giving me the best slot in the conference, because today's the summer solstice. And when you look at precisely when the summer solstice is, you see it's 8:50 p.m. UTC. Toronto is 5 time zones west of London, so that's 3:50 p.m. during my talk. But, okay, I forgot daylight savings time, so it's actually 4:50, meaning it's during the community building exercise. So instead, I'd like to thank the organizers for putting community building at the very center of this conference. All right, so let's go. What's the status of this? Joint work in progress. So the 5 of us have a proof of the theorem I'm going to tell you, but there's 2 or 3 corners we haven't written down. There may be gremlins lurking in those corners, if we do it very carefully. So if you don't trust me when I say theorem, here conjecture. Okay, but what's the setup? This is all right. So we start with a toric variety. Let's say smooth for convenience. Space in which I will write compact later. For story reasons, not now. Let's say it's d-dimensional. And inside this, we have a hypersurface arrangement, so we start with some hypersurfaces. Let's say n of them. So these should be irreducible, algebraic. Hypersurfaces in X. And so, and then you look at the complement of the collection of these things. So often in, I don't know, something like a moduli problem, if you're trying to hands-on build a moduli space, you have some setup like this. Your ambient thing might not be toric, but you have to remove some divisors, and then you want to compactify it well, and compactify the complement of these things well, and that's the kind of thing that we're trying to do here. Tell you about the Chowring of such a space. Particular examples, the wonderful compactifications. So there are 2 examples which kind of motivated us to start working on this project. So I'll give you the 2 key examples. They are, okay, so the first example is going to be hyperplane arrangements, and the attributions I'm going to give for these are not like the inventors of hyperplane arrangements, but the people who did the theorem that is like the closest precedent to what we're doing. Okay, so there's a theorem of Feichner-Jasinski that applies to hyperplane arrangements that we are generalizing. So how does this go? Okay, we're working in projective space. The HI are hyperplanes. So example of the example, all right, let's work in P2. I can draw in P2 if I pretend I'm working over R, which I will. My pictures are real style pictures. So you have some hyperplanes. Maybe you have something like this. Okay, I want, they don't have to be in any kind of general position. I can have triple intersections and things like that. Okay, P2, let's throw in the line at infinity. Okay, why not? There's the line at infinity. Okay, so that's an example of a hyperplane arrangement in P2. All of these things, I've put 6 hyperplanes in P2. So, all right, why this example? Because this example is M05, right? Okay, what's M05? I have 5 points in CP1. Infinity 0, 1 are the first 3 points. The other 2 points are not at infinity, not on 0, not at 1, and not the same, so not on this diagonal. So the complement of these things is M05, as Hannah told us about, and so M05 bar is going to be one of our wonderful compactifications, and this works for every M0n. So those are some examples of this example. I got into it more from a different angle. I sometimes identify as a combinatorialist. That is one of my genders. So there is a matroid story here. A matroid is a combinatorial object you can use to encode like how these hyperplanes intersect, what the codimension of the intersection of every subset is, say. That data is a matroid. And then there's this lovely recent work where you can build a matroid Chowring, and the matroid Chowring is also going to be one of these Chowrings. So that was sort of my way into this. All right, so that's one example, one class of example. another class of example is arrangements of subtori in a torus. And the nearest precedent to our theorem, although it's not exactly our theorem, they do things differently, they get a different description, is due to De Concini and Gaifi. So, okay, what are we doing here? Right, so I didn't write down the word compact yet, so I can just say X is the torus for now, and then HI are subtori, codimension 1 subtori, so like I pick a character and I say it has some fixed value. That's why I get a codimension 1 subtorus. Okay, so this would look something like this. Okay, so I have my, since I'm drawing real pictures, this is not an elliptic curve, this is C** squared. And then I have some subtori in here. Okay, so maybe I've got, let's say I've got one that wraps around like this. All right, that is some kind of like character xy cubed equals, I don't know, -1 or something. I don't have to go through the origin. They can be any subtori. Maybe I have one like this. Maybe I have one like this. Let's make a triple point. And some other points of intersection. So they're not subgroups, but they're cosets of subgroups. You know, okay, so the identity is going to use somewhere else. So they're cosets of subgroups in general. Right. And okay, so both of these things are going to satisfy the assumptions that we're going to have. So there's, you know, there are some nice combinatorics in this. There's a book of De Concini and Procesi called Hyperplane Arrangements, Polytopes and Box Splines, where, okay, the star is really not hyperplane arrangements as much as these toric arrangements, but where's the hyperplane arrangement? Well, if I take this real picture and take the universal cover, then I get a periodic hyperplane arrangement. And that looks awfully like the Bondel-Thompson picture people have been drawing. Is that the right name? Bondel-Thompson? So, you know, I bet there's a Bondel-Thompson connection here. Let's find it. But there's also, I mean, you can make enriched matroids for this setting, and you can tell some nice stories here too, like the story I'm telling now. And well, part of the thing I want to do is like, there are probably more examples to which this applies. So if you have a favorite hypersurface arrangement, you know, does it satisfy the condition I'm about to give? If so, let's talk. All right, so what's the condition that I'm about to give? Well, we need some kind of condition that says that the way my hypersurfaces intersect is going to be geometrically nice. So how do I want to do this? All right, let's say that the hypersurfaces are going to define something called the arrangement. So the arrangement won't just be the hypersurface, it will be something defined from the hypersurfaces. So let's say that the arrangement, thank you, Katzpar, so I will call this queer K, all right, will be the smallest set of closed subschemes of X that this definition is algorithmic, right? You should read it as it has the hyperplane, the hypersurfaces I want in it. And if I have two things in it, then if I intersect them, well, I don't just put the intersection in there, but I put connected components of that in my arrangement, right? So this is some recursive procedure. Intersect, decompose into connected components, put those in, pick two out, intersect, put into connected components, and do that until you've got all components of all intersections. That whole collection of subvarieties of all dimensions, I'm going to call the arrangement. So, right, as I say, it's a sort of, it's a recursive thing. And the assumption that I need to make is that the arrangement is what is called clean. In the literature, it means everything is smooth. I said scheme theoretic, everything is scheme theoretically smooth. Okay, so this is not much restriction on the combinatorics, but it's some restriction on the geometry. geometry. So okay, like, you know, I have these examples of like triple intersections of curves. Well, if any two of them give you a smooth point, then smooth point intersect the third is smooth point, no problem, right? I can take connected components, so something like this, 2 points, no problem. I just can't take non-scheme theoretically smooth intersections. I can't, you know, if my intersections are merely reducible but not disconnected, I can't do that, right? Okay, so if I have some kind of hypersurface or surface here maybe, and I intersect it with a plane, and I get like some reducible intersection, okay, but not disconnected, red X, this is bad. All right, so these are the kind of geometric constraints that this imposes, but, you know, combinatorics can be more or less what it will, but the geometry is mild-ish. It's like, I mean, the theorem is, the theorem about wonderful compactifications is that it's one blow up away from being very nice, from being normal crossings. Okay, so there's a theorem here that has been stated in sort of various levels of generality. So two people who have stated versions of this theorem are De Concini and Procesi in 95. Li in 2009, who was the one to introduce, like, I'm allowed to take connected components, a more global version of it, but there's many others, yes. Well, okay, the smallest arrangement, like what's the arrangement? I mean, right, okay, so it's, right, this is some kind of, I stated it universally, but you should, as I said, you should read it algorithmically. Take your hypersurfaces, intersect them all pairwise, take all connected components, throw those in.
Okay.
Take everything you've got, intersect pairwise, connected components, throw those in until you stabilize. That's right. Just do that. Yep. All right. So if you've got that, the theorem goes that these kind of things are like one path of blow-ups away from being normal crossings. So if you blow up a good subset of K, this is what's called a building set, and time-dependent, I'll tell you what a building set. But a building set is a good subset of queer K. You know, is blown up. You blow up each of the subvarieties in it, smallest first. Then you get a normal crossings result. The strict transform of the divisor. Is normal crossings. And these things are called wonderful compactifications, at least if they're compactifications. So like if my X is compact, this is called a wonderful compactification. So yeah, there are various examples of this in the literature. De Concini Procesi, I think, were motivated, I will say some words I don't understand, but by braid stuff, Vasiliev invariants of knots and monodromy representations of braid groups, and they found they could understand these things by doing a wonderful compactification of the braid hyperplane arrangement. It's Lee, I think, who did like arrangements of diagonals, including M0n. That's an example of a wonderful compactification. And so lots of people have found wonderful compactifications, one place or another. And right, so now I said I want X to be compact. I hadn't said that yet. The point is, right, in the first example of my two key examples, X is compact, in the second it isn't yet. So, all right, so let's fill in the thing I promised. Let's upgrade the assumptions that we live in a compact thing. So now sigma for complete fan. Didn't mention it, but it's a complete fan. And okay, let's also say that the toric boundary has to be part of our arrangements. We're forced to take that, toric boundary. So if R is the number of rays of my fan, then I've got these R toric boundary components. And I want them to be in there, and I want them to be input to this algorithm, so I have to intersect things with the boundary as well, and it should all be smooth. So, okay, well, this PD example, as long as all the hyperplanes don't intersect in a point, then like they're defining linear forms, there is some basis among them, and I can say that's the toric boundary, and I'm good, right? So there's really nothing to do. Here I just call some of the stuff the toric boundary. Here I really do have to pick a compactification. And so that was the first step of this De Concini-Gaifi work. They said, oh, well, you know, take a fan sigma, which is suitably refined so that none of the defining characters change sign on any cone of it. And then we got looking at this and we said, oh, this is actually tropical, right? So, I mean, flashback to Tuesday morning, we're doing tropical stuff again. Thanks, Rob, in particular, for, you know, defining all the things I need. So, except tropicalization, that will forever remain a secret, okay? But, so how do you get the X sigma in this thing? Well, you tropicalize the HI, and you get a hyperplane arrangement. In fact, in this case, you just get like, you pretend all these things were literal subgroups, and then you take the tangent space of the identity. Okay, you get that hyperplane arrangement. And then you take a fan of a smooth toric variety that refines that. And so that's, in terms of tropicalization, a very concrete way to get this X sigma, right? So here you'd have like 0, 1, 1, 0, and 1, 3, the way I've drawn it, as the slopes of your characters. Okay, so I have to smooth this thing out. Let's pretend that's a point. And I get some nice fan, which I can use as my sigma. Please.
Very naively, why not compactify by replacing X with, say, P1 to the power?
I mean, you can start by replacing X with P1 to the power of N. And then, okay, well, kind of geometric tropicalization says that now this thing comes through and it intersects one of these boundary strata, this one, at a point of multiplicity 3. So that's not a smooth point, so the whole thing's not clean. So I want to get this clean assumption. This is clean, and if I do it this way, this is clean. That's right. And the clean assumption is needed for the theorem. All right. Well, okay, in this case, I mean, Jared's suggestion was just use this thing. Okay, well, that's a, you know, I want a fan, you know, of which all of these hypersurfaces are unions of cones. Well, I'll leave the words here, but I have these hyperplanes now, tropicalizations. I said were hyperplanes. Well, in this, I could imagine filling this out to a complete fan. And now these rays are cones in it, so each of the lines is a union of two cones in the origin. That's what I mean. It should be a union of cones. All right. So, all right, I will probably get to state the crude and not very explicit version of my theorem in time, but that is perfectly all right. So what we want to do is give a way to describe the Chowring of a wonderful compactification. So we are going to use a piece of combinatorial apparatus. I mean, no one has defined fan yet, in particular me. So okay, let's start by defining multifan. All right, so generalization of fan. This is some work of Hattori and Masuda in 03 who were doing symplectic geometry with it. Okay, so a multifan is an abstract cell complex where the cells are polyhedral cones and it's endowed with a map to Rn, R sum n, big N, that is cone-wise, linear, and cone-wise injective. Okay, so cone-wise linear means I have a bunch of cones in Rn, but cone-wise injective means they can intersect or lie on top of each other in funny ways in Rn, right? So the kind of thing I'm allowed to have maybe I have two rays, and then I take, the cone between them, and then I take another cone between them, and these are two different abstract cones, but I just map them to the same thing in Rn. So I'll draw it as this kind of like banana cone, but this is two things that are mapping to the same thing. Perfectly all right, it's cone-wise injective. Or, maybe I have two cones that like intersect after embedding. I have this cone and this cone, and I embed them in R3 like that in such a way that, they share this line. That's not a face, but it's still cone-wise okay. So these kind of things I can do in multifans. If I had said globally injective, that would be the definition of a fan. But I only need cone-wise injective. All right. So Champagne in 2006 said that if I have a rational multifan, so one where all of these polyhedral cones map to rational cones, let's call it sigma hat, then I get an associated toric variety that's made by gluing the same way Fulton says how to do. Call it x sub sigma hat, and gives a presentation which is explicit, and we'll see if I get there. No, the answer is no, of A star Chowring of x sigma hat. If you know the usual presentation of a Chowring of a toric variety of a fan, it's kind of like that, but I can't just use rays as generators because like rays don't uniquely determine a cone, so I have to have a variable for every cone, and that necessitates a change in the form of the relations. But it's like that. And okay, kind of the key thing about the geometry of this thing, okay, so it might not be compact because the fan might not cover all of Rn, that's familiar. But it might not even be separated. That is what happens when you have these cones that map to the same place. You get non-separated structure because I'm like filling in the same limit of some one parameter subgroup multiple times. You get non-separated schemes when you do this. And so that guy is our main apparatus for giving our description of the Chowring. So theorem, like I say, you trust me, right? I can write theorem. Okay. So what do? We give an explicit combinatorial multifan, rational multifan, sigma hat. What does it do? All right, the first thing it does is be the dual boundary complex of the wonderful compactification. So it tells you what all the exceptional divisors are in this blow-up and how they intersect. Oops, well, I need 4 any wonderful compactification. That's the point, right? I introduce these wonderful compactifications. So if I have a clean thing, then I can make a wonderful compactification. Now, what does it do? All right. So, as I was saying, this thing, Toby told us about dual boundary complexes briefly. So, thank you. So the dual boundary complex of the wonderful compactification. So it's minimal non-trivial faces, in this case the rays. The rays correspond to the various divisors you get, the pullbacks of the HI and the exceptional divisors. And there is a cone for every component of an intersection of these boundary divisors in the compactification. That's what it means to be the dual boundary complex. Okay. Now, next we'd like to say something like, oh, well, you can get W as a closure. There was a theorem like this in De Contini Procesi, for instance. They gave you a way to get W not just as this sequential blowup, but also as the closure under some particular embedding. So we want to say that, but our tool is this X sigma hat, and that's not separated. If you take a closure and a non-separated thing, will be non-separated. Well, we don't want that. So, okay, we have to do do something a bit more delicate than the closure using this combinatorics. But the point is, okay, so I can take C star to the D, the torus in my X, which also embeds in my W. And now I can put W into this X sigma hat. And I'm not going to say it's the closure of the image of this, but we can put it in, in a very explicit way. What do? This is a map. In fact, it's going to go into a D plus n dimensional torus. This is going to be a D plus n dimensional multifan. How? First D components are the identity, and then the next D components are just the defining equations of the hypersurfaces. So if the HI is the 0 locus of Fi on the torus, I just move all the hypersurfaces kind of to the toric boundary, stick that in the D plus n torus, partially compactify using the directions of the cones in here in the geometric tropical compactification rather sense that Rob told us about. Like each cone tells us a limit direction that we need to put in to get some of W. And then you take the cones indexed by that combinatorics, not the whole closure, and that's how you get W. And part 3 of the theorem, okay, I'll stick that up here. Part 3 of the theorem is that, yes, this gives you the Chowring of W. Okay, well, we get it from Payne's description of the Chowring of X sigma hat. W sits in X sigma hat, so there's a restriction map here. And all right, in some very nice cases, it's equal. For instance, one of Juni-Ha's theorems is that if you are in the hyperplane arrangement setting, this thing is actually an isomorphism on the node already. But in general, we have to do a bit. This thing is smooth, so it should have Poincare duality. And so I don't have enough time to say more than this. What do? You quotient by like an annihilator of what should be the explicit fundamental class. What's the fundamental class? This is the, under the Minkowski weight description, this is just the weight 1 on each maximal cone of X of O sigma hat. So via this Payne description, putting weights on each maximal cone describes a map from the top, or from AD plus n of this thing down to Z. This is a tropical fan, so it's balanced. That says it actually defines a well-defined map from this Chow group. We heard what balancing is thanks to, I forget who said balancing. I'm embarrassed. Someone told us what balancing is in the tropical sense. We have a nice balanced weight here. We mod it by its annihilator. We get the Chowring. I'm out of time. Thank you.